Let us start from previous lecture. We started with the type of different materials. During last lecture, we discussed about the various types of materials. Inside that, we have seen what is meant by isotropic material, what is transversely isotropic material, monoclinic material, orthotropic material, and anisotropic material. So like these different types of materials we discussed during last lecture. And now we are going to observe the Hooke's law, how it is applied for the different types of materials. In general, the relationship between stress and strain, so that relation which is given in the form of matrix form, so stress related to strain, and here whatever the matrix is shown, that matrix is called as the stiffness matrix. Is it okay? So you can see the each and every elements. So starting from C11 to C66, C11 to C16, C21 to C26, C31 to C36. Likewise, each and every element, how it is related. So stress and strain, if these are related with each other, then with that relationship of stress and strain, each and every parameter is taken into consideration. And with respect to that particular parameter, for example, if we take the relationship between sigma 1, then all the parameters, if suppose C11, then C11 is related to epsilon 1, C12 will get multiplied with epsilon 2, C13 multiplied with epsilon, first row and first, so these all these row elements, so first row elements, and that will get multiplied with this column element. So each and every time, each corresponding row and corresponding column element will get multiplied with each other, and with that multiplication, whatever the final result we will get, that will be the stress. So relationship between stress and strain, so that is dependent upon these various parameters C11 to C16, likewise for sigma 2, C21 to C26, like this. Is it okay? So for isotropic material, how many parameters, minimum how many parameters are required? For transversely isotropic material, how many parameters required? Now that is the interest of today's lecture. So what can be this maximum element if we consider this particular stiffness matrix? Is it okay? So if we consider this stiffness matrix, then for stiffness matrix, maximum elements are 36. So this C matrix, 6 by 6 size of the matrix is there, and maximum constants that are 36 present over here. Is it okay? So how, if we consider that the worst material present inside the universe is there, for that worst material inside the universe, which is non-homogeneous, which is non-isotropic, like this, for that material maximum 36 constants are required. So each and every constant, each and every direction, each and every point for these materials will be different, and that's why in that case we will require 36 constants, because in isotropic material we always say that in order to represent the behavior of the material, we required only two elastic constants. In general, for the isotropic material, we consider four elastic constants: E, mu, Z, K. E is the Young's modulus, mu is Poisson's ratio, G is shear modulus, and K is the bulk modulus. So these four parameters which are considered to be independent parameters from each other, but there is dependency in isotropic material, because we know the relationship between E and Z, E and K, E is equal to 3K into bracket 1 minus 2 nu, like this relationship we have established. That's why if two parameters are known, then remaining parameters we can identify. So for isotropic material, we require only two constants in order to have the relationship between stress and strain. Similarly, in order to represent the relationship between strain and stress, if suppose I want epsilon 1 in terms of sigma 1, sigma 2, sigma 3, like this, if this is the first row, and if that first row is related with this first column, then first row, first column, that particular multiplication will give the epsilon 1, and that epsilon 1 here will be considered to be the answer of this first row and first column. Previously here we have considered this as a stiffness matrix. Is it okay? And for this we are considering to be a compliance matrix. So this represents S11 to S66. All these 36 constants are shown here that are represented by the compliance matrix. So what is stiffness matrix and what is compliance matrix? That now we know here from this particular relationship between stress and strain and relationship between strain and stress. We know now the compliance and stiffness matrix and how these are related with each other and how to identify them. So during last lecture we also seen that how to identify these elements of the compliance matrix. S11 is the element of the compliance matrix. S12 is the element of compliance matrix. Likewise, S44 is the element of compliance matrix. Like this, suppose here it is considered, means in short, if we consider the material is isotropic, then definitely S11 is 1 upon E that we have seen during last lecture how it is. Then S12 is minus mu upon E. How this S12 is, that also we have seen during the last lecture. S44, S55 and S66, that is nothing but 1 upon Z. So that is given here. So 36 constants, that are the maximum values in order to describe the stress and strain relationship. With the generalized equation which is shown, the total matrix is replaced by this generalized equation. And this 2.28 represents the generalized equation which gives that this sigma I is equal to summation of j is equal to 1 to 6 C I j. C is represented as a constant which is multiplied to this strain. Is it okay? So each and every value of j is equal to 1 to 6. J is changed from 1, 2, 3, 4, 5 like this. I is equal to 1 suppose. C11, C12, C13 like this. This will going to change here. Is it okay? Then in contracted notations, suppose the notations are contracted notations, then here we have used the term tau 23 which is replaced by sigma 4, tau 31 which is replaced by sigma 5, like this. Epsilon 4, epsilon 5, epsilon 6 means stress and strain, so that are represented with these notations in a contracted matrix. Likewise, now the values of these stresses and strains and the strain energies that can be identified. Now come to the first kind of material, that is anisotropic, because step by step we will move from anisotropic to isotropic. So if we consider the anisotropic material, then the material that has 21 independent elastic constant at a point is called as anisotropic material. Is it okay? See, the maximum independent elastic constants are 36 from C11 to C66 that we have seen now. But in anisotropic material, it never happens that there required the 36 elements. Though material is anisotropic, here only 21 independent elastic constants at a point is required, and that then this material we can consider as an anisotropic material. Is it okay? The type of material for which to define we require 21 independent elastic constant is called as anisotropic material. Then once these constants are found for a particular point, the stress and strain relationship can be developed at a point. Now suppose this is a particular any material plate, and this 1 1 dash 2 2 dash 3 3 dash, how see 1 opposite to that 1 dash, 2 opposite to that 2 dash, and 3 opposite to that 3 dash. If we take the direction into consideration, then we'll come to know that constants are found for a particular point. The stress and strain relationships can be developed at a point. So here we'll have to note that these constants can vary from point to point if the material is non-homogeneous. Is it okay? So two things are different. That isotropy and homogeneity, that two things are different. If material is non-homogeneous, then point to point properties will change. But if material is anisotropic and homogeneous, is it okay? See, we are making combination of two things, isotropy and homogeneity. When we consider the material is anisotropic, here Anisotropic, that means that the for each and every direction properties are different. Is it okay? Suppose for one direction is here, properties will be different. Then for two, properties will be different, and for three, the properties will be different. Is it okay? So that represents the anisotropic. But if we add the term non-homogeneity, then meaning of non-homogeneity is that the here we will require to define the different points. For each and every point we will have the different properties. Is it okay? So anisotropy and non-homogeneity, that two things we will have to take into consideration. So even if the material is homogeneous, one needs to find the 21 elastic constants. Means here if material is anisotropic and homogeneous, then 21 properties are sufficient to define the material. Is it okay? For each and every point, one need to find these 21 elastic constants analytically or experimentally. However, many natural and synthetic material do possess material symmetry. That is, elastic properties are identical in direction of symmetry because symmetry is present in internal structure. Fortunately, this is symmetry that reduces some of the constants within 6 into 6 stiffness. So 6 into 6 stiffness matrix and 6 into 6 compliance matrix. The simplifies Hooke's law relationship for various types of elastic symmetry. So what is the conclusion in anisotropic material? The material is anisotropic, but it is homogeneous type of material. We are not considering the material as non-homogeneous. By considering material as homogeneous, we are considering the properties of that material will be 21 independent elastic constants are sufficient in order to define. Is it okay? So anisotropic material, but here homogeneous material. By considering anisotropic and homogeneous, 21 elastic constants are required. So that we will have to keep into mind. Is it okay? Now, as far as concerned with this anisotropic material, now we are moving further to the monoclinic material. So, if one plane of symmetry, material symmetry, see here, this is monoclinic material. Is it okay? Here, this material is considered to be monoclinic material. So, monoclinic material, how it is defined? One plane of material symmetry. Direction 3 is normal to the plane of material symmetry, then stiffness matrix reduces. Means in monoclinic material, what happens? This is the plane of symmetry. For third direction, for 3 and 3 dash, properties are same. For 2 and 2 dash, what is going to happen? Suppose for this direction, whatever the direction shown here in this direction, now particularly in this direction for 3 and 3 dash, what is going to happen? For this direction from center in upward direction, the properties, and from center to this particular direction, properties are remaining same. Is it okay? This is one plane of symmetry. We are saying this is the plane of symmetry. For this, the material properties are remaining same here. Is it okay? So see these two directions. First direction upward, second direction downward. This we will call as a material of symmetry here. But in this case, if we consider in this direction 1 1 dash, particularly the direction which is right hand and the direction which is toward the left hand, in both the direction, to the right hand and to the left hand. So if we consider these two directions differently, right and left directions, then the properties here are different for this one direction and for this one dash directions. Is it okay? Likewise here also it can be happen for this two dash also. But 3 dash is considered to be plane of symmetry here. So this total 3 to 3 dash, this particular will be the plane of symmetry here. Is it okay? Then in one plane of material symmetry, so direction 3 is normal to the plane of symmetry, then stiffness matrix. So stiffness matrix that we have seen that C11, C12, C13, C14, C15, C16, like this we have already represented. In case of anisotropic material, we have considered that there are 21 number of the constants are required in order to represent this. Is it okay? Now here you can see how these number of constants are there? 1, 2, 3. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Here we can see 4, 4, 4, 12. This 4, 16, and this 4, 20. So this is now reduced here. Now what is going to happen here? See. C14, C15. What is shown here? C14, C15, C16. What is exactly happening here if we consider, if we bring into mind that the stress-strain relationship is there, then this particular C11 is related to this particular multiplier. In order to have this particular relationship between stress and strain, whatever the matrix we have considered as sigma and epsilon from C11, it is always multiplied with epsilon 1, C12, epsilon 2, C13, epsilon 3. C14, that is related with this gamma. This is the shear parameter. C14 and C15, that is considered to be shear parameter. Now, in monoclinic material, exactly what is going to happen? That this C14 or C41, both are same. Is it okay? C14, C means 1 to 4, the material parameter which is related to direction. What is the which will be the middle parameter in between 1 and 4? 1 to 4, 1 to 5, like this 4 to 1 and 5 to 1. So these two parameters here, C14 and C15, likewise C41 and C51. These two parameters, if we take into consideration, that becomes 0 here. Is it okay? Likewise, C24, C25. Is it okay? So here, if we consider, this is C14, this is C15, this is C24, C25, and then C34 and C35. Same elements are repeated here also, because C14 is here, it is C41. C14, if it is 0, C41 is also 0. C15 is here, then C51, which is also 0, opposite to C14 is same as C41. Is it okay? So like, because Cij is considered to be equal to Cji. Likewise, these corresponding elements here, C24, whatever we consider here, C24, which is present here also, C24 and C24. So like this, if we consider these two elements will be considered to be 0, C25, and here it is C25. That two corresponding elements also we are considering to be 0, C34, which is present here, C34, C35, here it is considered to be C35. The corresponding elements are considered to be equal to 0 here, and that represents that these particular parameters which becomes equal to 0, that are now, if we try to identify the relationship, if it is stress sigma 1, then epsilon 1, epsilon 2, epsilon 3, this is the parameter which is multiplied to epsilon 4, epsilon 5. Likewise, whenever we are calculating here sigma 4, then for sigma 4, this particular row we are going to take into consideration. This particular row will taken into consideration for calculating the sigma 4. So for calculating sigma 4, we don't require these three material parameters, because in monoclinic material, as there is one plane of symmetry here, as this is the plane of symmetry here, so these material parameters are going to not making any significant role, which is considered to be 0 here. Is it okay? Similarly, C46 is going to 0 here, C56 is also going to become 0 here. Is it okay? So like this, C46, C56, that is going to become 0 here, C14, C15, C24, C25, and C34, like this, from this C14 to this C56, all these C are going to become equal to 0 here, because we have considered is a one plane of symmetry here. Is it okay? By considering this one plane of symmetry, we are getting the corresponding parameters as equal to 0. The direction perpendicular to the plane of symmetry is called as principal direction. Note that there are 13 independent constants which are sufficient here. Now, though here we are going to observe the parameters as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. But exactly if we count, we will come to know that there are only 13 parameters, because C11 is different, C12, C13, here it is C16 is present. That C16 which is represented here, if we consider here C16, same C16 is present here, because C16 is nothing but 6C1. Here 61 and 16 means the parameter which is in the direction of 1 and 6, same will be in the opposite direction. Cij is equal to Cji. Besides, if it was 6C61, now that is replaced by 16 only. Similarly, here 26 is there, so this is repeated here. Means 61, 62 and 63. All these three parameters which is shown here. So these three parameters which is shown here, same three parameters are shown here also. Is it okay? So C16, C26 and C36, like these three parameters, C16, C26 and C36, which are here, C66 are here only. Is it okay? So if we try to understand the number of, if we will try to count exactly the number of independent elastic constants required to represent this material, then C11 is here 1, 2, 3, 4. Here it is counted here only, because C21 is nothing but C12. That's why this particular is that represents the homogeneity. As here C21, if we represent this C21 differently, C22 different, then that represent this is the non-homogeneous. But we have considered the material as homogeneous, though it is anisotropic, homogeneous, the monoclinic homogeneous. Is it okay? So that's why C12 is same as C21 only. So 4, then here 5, 6, 7, then this is already covered, this is already covered, 8, this is 9. Is it okay? Then 10, 11, this is already covered, 12 is here, this is already covered, this is already covered, this is already covered, C36 is here, and this is 13. Is it okay? So if we count the particular parameters for monoclinic material, we will come to know 1, 2, 3, 4. These are covered. This is 5, 6, 7. This is covered, because 1, 3, which is present here also. The 2, 3, which is present here also. Yes, yes.
Hello, sir.
Yes. Yes. You are audible. Yes, any doubt? Okay. Now is it clear? Now voice is clear. Am I audible?
Yes, sir.
Okay. Okay. See. So if we try to count them, then after counting we will come to know that for the first row complete, these are the 4 elements: C12, C11, C12, C13, C16. Then in second row C12 is already covered here, C22, C23, C26, 3 elements. So 1, this 4 and this 3, 7. Here if we consider 1, 3 is already covered here, 2, 3 is also covered here, then 3, 3 and 3, 6. These two will be new, here we will consider. 4 plus 3, 7 plus these 2, 9. Then this C44 is 10, C45 is 11, C45 is already covered here, this C55 which is new here, this is 12, C16, C26, 366 are already covered here in this particular column. This total row is present and new material is C6. So how many constants are there? Total constants if we'll count, then this count is totally 13. Is it okay? So 13 independent elastic constants are required in order to represent the monoclinic material. So feldspar is an example of monoclinic material. Is it okay? Feldspar is example of monoclinic material. Is it okay? So this way, now we may have the relationship between the stresses and strains. So two type of materials we have covered now, out of which the first type of material we considered is the anisotropic. Second type of material we considered is monoclinic material. But in both the cases, in case of anisotropic material, we require 21 independent elastic constants. In second category of material, in monoclinic, we require the 13 independent elastic constants for any point in order to represent the properties of the material. Is it okay? Now, as far as concerned with this particular orthotropic material, third category of material now we are observing here. So, for orthotropic material, what we are considering, if a material has three mutually perpendicular planes of material symmetry, then the stiffness matrix which is given. See here, for orthotropic material, orthogonally anisotropic, specially orthotropic. If a material has three mutually perpendicular planes of material symmetry, then stiffness matrix is given here. Now see what is changed in orthotropic material exactly. So here, do understand first of all what is meant by orthotropic. As name suggests, ortho means perpendicular. If the properties of the material are remaining same in perpendicular directions, means suppose if we consider that in direction 1 and in direction 2 properties are same, but in direction 3 materials properties are not same, then that case in one direction properties remaining the same, but in two directions material properties are remaining same, but in one direction is changing only. Is it okay? In that case, that kind of material we are considering as orthotropic material. Is it okay? If a material has three mutually perpendicular planes of material symmetry, then the stiffness matrix is given as, so here you can consider how it is calculated, how it is given. C11, C12, C13, then 30. C12, C22, C23, then 30. Likewise, if we consider how many number of elements are actually related with each other, these 3, 9, 10, 11, 12. But if we identify the common material from them, but common material parameters in between them, then we will come to know C11, which is present here, then 12 is present here, 13 is present here. But here 12 is already covered. Two news are 22 and 23 are present here. Is it okay? So that means in the first row we have three independent constants, elastic constant. We are considering them as elastic constants. Then these 3 plus these 2, 3 plus 2, 5. Then here 13 is over because 13 is present here only. Then 23 is over because 23 is present here only. So 13 and 23, these two are covered here. Then 33, that is present. So that means here 3, here in this row 2, and in this row 1. So 3 plus 2 plus 1. Is it okay? So 5 plus 1, 6 parameters in this first 3 rows. Then C44, C5 and C66. These 3 are different here. So that's why the 6 parameters from these 3 row and these 3 parameters, 6 plus 3 is equal to 9 parameters that will are required here. So here the 9 independent parameters are required. Is it okay? So in order to have the representation of this orthotropic material, in order to represent the orthotropic material, we required 9 independent parameters. Is it okay? So here you can consider that the compliance and stiffness matrix, out of which from this S11 to S66 that will be the S matrix, and for C11 to C66 this is the stiffness matrix. So stiffness and compliance matrix, which is represented, which is shown here for them, these are the different deformations and these are different materials here. Is it okay? So likewise, we should have the relationship between the stress and strain. And then we consider that for orthotropic material we required 9 materials. Is it okay? So wooden bar, rolled steel, these are the example of this kind of orthotropic material. Is it okay? Then if we come to the next type of material, then it is considered to be transversely isotropic material. So consider plane of material isotropy, and in that, in one of the planes of the orthotropic body, if the direction 1 is normal to the plane 2, 3, is it okay? So here you can consider transversely isotropic material means what? If we consider here transversely isotropic material, that one of the planes of orthotropic body, if direction 1 is normal to the plane 2, 3 is isotropic, means again in first case in all direction properties were different. In monoclinic one direction was there, in orthotropic two direction properties were same. Now here if material symmetry is there like this, if suppose we consider the symmetry from this corner to this corner, and there if these are transversely isotropic, in transverse direction these are isotropic, one more direction is considered here, then we will have this particular independent elastic independency that will get reduced again, because here we know C11, C12, C13 earlier we were using, now we are using C12 only. Is it okay? Then C22 and C23, these are the two different parameters, elastic constants we consider. So here 3 plus these 2. So here not 3, here only 2 only, C11, C12, C12. So 2 plus 2, 4. Is it okay? Then remaining are covered here. This can be calculated from this C22 and C23. So 4 are here and this one is 5. So in transversely isotropic material, 5 independent elastic constants that are sufficient. So in first case, when the material properties which is considered to be a anisotropic, at that time what has happened, we have considered for anisotropic 21 independent elastic constants are sufficient. Then in second case, when that we considered a monoclinic, at that time we consider 13 independent elastic constants are sufficient. Then in third case, when we consider this as transversely isotropic, then 5 independent elastic constants are sufficient. And then if we consider the isotropic material, then for isotropic material we know that C11 and C12, only these two parameters will be used here, and that's why for isotropic material only 2 elastic constants are sufficient here. If we identify the stress strain relationship here, we can see here C11, C12, C12 is only there. Similarly, C1, C12, C11, C12 is here. That means what it represents? It represents that the material, if it is isotropic material, then only 2 constants are sufficient in order to establish the relationship between stress and strain or strain and stress. Is it okay? So for isotropic material, what is C11? C1 is E into bracket 1 minus mu divided by 1 minus 2 nu 1 plus mu. C12 is equal to mu into bracket E into 1 minus 2 nu 1 plus mu here. Is it okay? So likewise, for C11 and for C12 here, this kind of relationship we are going to establish with this one, and then we can get the C11 minus C12 upon 2 is nothing but G here. Is it okay? So this is nothing but G here. This is G here. C11 is nothing but 1 upon E, that already we know here. How we have identified C11, E into bracket 1 minus nu into bracket 1 minus 2 nu 1 plus nu here. Is it okay? So likewise for compliance matrix, and here we have considered, besides C we are using the notation yes here. Is it okay? So C is the notation used for the stiffness matrix, yes is the notation used for the compliance matrix. For compliance matrix, that is the relation between strain to stress. For stiffness matrix is relation between stress to strain. Is it okay? So likewise, if we take the inverse matrix of this particular, then we will come to know that this inverse matrix is nothing but this compliance matrix here. Okay, so inverse and compliance matrix, that two matrices which are represented here and which are given here, in order to have the relationship between them, that is shown here. Is it okay? Then as a summary of that, if we try to identify how many number of inelastic constants are required and which category of material, then we will come to know that anisotropic material 21 independent elastic constants are required. Is it okay? For monoclinic material, 13 independent elastic constants are required. For orthotropic material, 9 independent elastic constants are required. For transversely isotropic material, 5 independent elastic constants are required. For isotropic material, 2 independent elastic constants are required. Is it okay? So that is very important, which we should know, because in many cases for getting the MCQs, definitely one question is asked on this particular part, that for anisotropic material, how many number of elastic constants are required in order to establish the relationship between stress and strain. In case of monoclinic material, how many number of these constants are required for orthotropic and for transversely isotropic to isotropic. Is it okay? So this case we have resolved from anisotropic and non-homogeneous to anisotropic, homogeneous, monoclinic, homogeneous, orthotropic, homogeneous. First of all, 36 number of parameters which is required. So that 36 represents anisotropy and non-homogeneous material. If non-homogeneity is removed, then only anisotropy remains. Anisotropy and homogeneity, for that 21. Then monoclinic and homogeneity 13, orthotropic and homogeneity 9, transversely isotropic and homogeneity 5, and for isotropic and homogeneous, there two only parameters are sufficient in order to have represent the behavior of the material. Because with the help of this particular elastic constants only, what will be the value of stress, or what will be the value of strain, what will be the displacement, what will be the deformation, these all terms that can be identified. In actual practice, which material is used for which particular application, if besides our regular material, if composite material is used, and if that composite material is in monoclinic category or orthotropic category or in transversely isotropic category, then how a particular material will behave. Because already I discussed previously that no software is available in the world which will define all these materials together. Because for each and every software there is particular assumptions working on all this particular category anisotropic to isotropic, this is not available presently also. For this subroutine files are required to analyze any material. So there are different theories, may be considered first order theories, higher order shear deformation theories. These theories are required in order to establish that relationship between stresses and strains, because here we are considering anisotropy, non-homogeneity, again non-linearity also sometimes that are present here. Is it okay? So these things we should understand in case of composite material. That is very very important as far as concerned with this the macro mechanical. Is it okay? Purposefully we are using the word macro mechanical analysis of lamina. In case of micro mechanical analysis of lamina, we are taking the different standards, we are referring the different standards. But whenever we are understanding the concept of macro mechanical analysis, then for this macro mechanical analysis of any lamina, definitely we will have to take the support of all these constant elastic constants. So that particular lamina have a behavior of anisotropic, monoclinic, orthotropic, transverse isotropic or isotropic. Based on that particular behavior, the relationship between stress and strain will get established, and that particular relationship between stress and strain will represent that which kind of material, which type of material it is.